Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. This video is a continuation of our previous discussion on the topic of transfer learning. In fact, in the last tutorial we looked at how we can use VGG16 without training on any of our own images to load an image, to actually classify an image that we just downloaded from the internet. And the one before that, we actually talked about colorizing black and white images using autoencoders, although we didn't achieve great results with some of the autoencoders we tried. That has to do with the limited training images that we actually got. Now, to accelerate this process, again, as I mentioned in the previous tutorial, you can actually augment the images, meaning you can actually rotate, translate, flip, and do a lot of tricks to your images that you already have, but that's going to help you, or that's going to take you so far. Now, transfer learning helps you, as the name suggests, transfer the learning that you have from some other situation and then apply it to your own situation. So in this case, let's actually take VGG16 part of it and then add our decoder to convert this VGG16 into an autoencoder decoder that actually does the colorization of black and white images. And graphically, this is how it looks like, so we have our VGG16 architecture, and again, as previously discussed in the last tutorial, the first part of this, in fact, if you count this, it would be exactly 19 layers. The first 19 layers, they're all convolutional layers, so these are all feature extraction layers, and the next layers that follow are the classification layers, and with an output layer that's actually predicting 1,000 different classes. And the classes are tennis ball, is it a bus, is it a race car, and so on. We are not interested in doing any of this part for this exercise, because today we are going to talk about encoding autoencoders and to actually colorize black and white images. So let's actually import this VGG16, but not like the last time, not the entire model, but only up to this point, only the first 19 layers, okay? And then let's actually add, once we, I should have chopped this part off in this graphic, but add this, our own custom decoder to this part over here. Okay, so this one says 7 by 7 by 512. Okay, so we're going to add this part from this point, which means the input that goes into our decoder is of the size 7, 7, 5, 12. So when we define it, we have to keep that in our mind. And eventually what we are trying to achieve is achieve two outputs, right? I mean, our input is a color image. Well, actually it's a black and white image, but during training we are actually taking this color image, separating the L channel, which is the lightness. We're taking an RGB image, converting that to a lab image, LAB. L stands for lightness, A stands for, I believe it goes from green to red, and B channel actually goes from blue to yellow, or one of those. But A and B contains the color information, L contains the lightness information. So L is a black and white image. So we're going to send this and A and B. So meaning the final layer is going to predict A and B channels and apply that to our L. Okay, so what we are predicting is color from this autoencoder. Now let's make more sense out of this by jumping into the code, and actually let's go ahead and code it again. As usual, I've written this in our in a notepad, and I'm just going to copy chunk by chunk while explaining the code. And I thought that's the best way to use your time, or to spend your time in learning. So let's switch to Spider interface. What I meant to say was, let's switch to the Spider IDE, and here we are. So the first thing what we need to do is actually get the VGG. So here you see from the last tutorial, these are the, let's go ahead and do this, okay? Let's copy these lines, let's paste them here, and instead of model, I'm going to just call this VGG model, okay? So let's go ahead and run these lines, and the first time, as I mentioned in the last tutorial, it's going to download this entire VGG, which is 600 megabytes, so it's going to take a little while. So let's go ahead and run this code for now. Okay, so it didn't take that long because obviously I've already done this once. So I have the VGG, and it's got a lot of layers, as you can see, 1, 2, 3. You can go ahead and count it, but all the way down to flattening, and then the couple of dense layer and the prediction layer, where it predicts 1 out of 1,000 of these different classes. Now, what we really want is to chop it off at this 7, 7, and 5, 12. I think that's what we have, right? So if we go back to the graphic, we need to cut it down to this point, 7, 7, 5, 12. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18. Okay, so we want to chop it off at the 18th layer. So the way we do that is, let me go ahead and remove this part over there. And one other thing, what do we do after chopping it off? Well, actually, let's, we can chop it off, but I want to assign that part to a new model. So what, again, so I don't confuse you, I want to cut it off up to here and assign this to a new model. And then to that model, we are going to add our decoder. So in a way, I'm going to define a new blank model, take the layers from here and take the layers from our decoder and add them into this new model. So I'm going to call this new model, what shall we call the new model? Let's actually call it new model. Okay, so and how do we create a new model? Again, actually, let me go ahead and copy from my previous file all of these libraries, because the way I like to add layers is by using sequential here. Okay, is by using sequential. That's part of Keras. So my new model is sequential. There you go. So now my new model is empty model as of now, but I'm going to add whatever the chopped off layers that I get from VGG to this new model in a minute. So how do we actually take a subset of this VGG? Well, you can look at the layers. You can actually enumerate. So in fact, I have a few lines of code here. So what we do is, just a second, let me paste it. So in VGG model layers, we are actually looking at, okay, if I is less than 19, which means up to 18, okay, add the layer to this empty new model. Okay, so that's exactly what this is. And at this point, we can actually go ahead and have a look at the new model summary. And hopefully we will see only up to this point, 7, 7, and 5, 12. Okay, new model dot summary. And let us, I think we did those parts. So let's actually run these lines. Here is not defined. Oh, sorry, I didn't include that. Okay. Okay, I'm sorry. We added a whole bunch and forgot to run those. It doesn't know that, okay, I'm importing these libraries. By the way, I'm not running the entire code because I don't want to download this VGG16 again. In fact, the last few times I tried in Spider, if you already downloaded this once and you're running this again, it has a tendency to crash the console. That's why I'm trying to stay away from doing anything to this once I downloaded this, okay? So anyway, so now that we have that part, now let's go ahead and run it. Okay, there you go. Our new model, actually the last layer in our new model is 7, 7, 5, 12. So it's exactly the same that we have here, except we do not have these dense layers and the flattening layer over there. Okay, so far so good. So this is again part of our exercise doing the transfer learning, right? So we want to transfer our learning, not just the model, but the weights associated with that up to this point, okay? By the way, how do you say you want to use weights, or do you want to train this using new, using new data? So here it is. So for each of these layers, is it trainable? No. False. That means I do not want to train these layers again, meaning use the weights that actually they came with. Okay, do not update the weights over there. If you want, you can. Okay, you can take it and you can go from there and you can update the weights, but let's not do that. Okay, so that's it. So now again, I'm copying some of the code that we already have from our image colorization a couple of lectures ago, so go ahead and check it. So our path is images / colorization. So if I go to our images colorization, I have a whole bunch of images here that I'm going to use, convert them to grayscale, like I mentioned, extract the L channel, use it for training. Okay, so how do we do that? Well, in fact, even before doing that, let's actually convert these into the right size. Okay, so here you go. Sorry about this. Let me expand the right hand side so you can see this better. Okay, so again, I'm using trained data gen. This is nothing new. I covered this a couple of tutorials ago. We are rescaling these values to values between 0 and 1. Because our RGB image, the values are between 0 to 255. I'm dividing them to by 255, so the values are between 0 and 1. And why do I want them to be between 0 and 1? The activation functions that we are going to use for these for this channel is ReLU activation that goes from 0 to 1. Okay, and for A and B channels, the activation actually the values for A and B, they go from -127 to +128 for these channels. Again, read up on lab image formats if you are interested in this. LAB. L stands for lightness, A and B are the color channels. Okay. So for those A and B, the values go from -127 to 128. So we will have to divide that by 128, which we'll do in a minute. But for now, let's just look at step by step. So what we're doing is taking these images and then rescaling them to values between 0 and 1. Once that is done, okay, we are changing the size of these to 224 and 224. If you remember in the previous tutorial when we did the colorization, I changed them to 256 because that's just a random number. I wanted to, small enough that I wanted to change the images to. Now, why 224? The pre-trained VGG model, all the images are 224 and 224. If you look at this, the input, it's expecting us to input an image that's 224 by 224, right? Otherwise, it's going to throw an error. So that's exactly why we should be converting our images to a size 224 by 224, and everything else is pretty straightforward. Okay. Now let's convert these images into lab format. Until now, these are all RGB. In fact, let's go ahead and run these new lines of code that we just got, and you can see, okay, we have the image training path, and now let's actually again exactly the same code I had from our last tutorial, which is defining an empty array for X values and Y values. And X values, we are going to use our L channel, which is the lightness values, okay, from our input images, and Y is going to be the color channels, which again is later on in this step. We are converting our input images, okay, for image in this train, right? We are converting them from RGB to lab, okay? So, and then extracting the first channel, which is L, and appending it to this empty array X. Same thing, extracting channels 1 and 2 and dividing these by 128. Again, I just explained that. A and B channels in a lab image, they go from -127 to 128. So to force our Y to be between -1 and 1, we are dividing this by 128. Okay, this is specific only to this example if you use this RGB to lab conversion and all of that. Okay, don't get confused with all of these. So transfer learning, pretty straightforward. These are minor details in terms of how we are handling our data. And we are reshaping to a dimension that is appropriate for our neural network over there. So let's go ahead and run this one more time so you can actually see what we mean by reshaping it. So we actually converted our images into an array and then reshaped it so it's defined as 32 by 224 by 224 by 1. This stands for 32 images, okay, and 224 by 224, and 1 is the L channel that we actually have. And the same thing here, 32, 224, 224, and 2. Okay, so that's what we have here. And the next thing is we can, I think we're almost all set. Now the only thing here, if you look at the X, where is it? So when we send this into our VGG, the VGG input, actually, if you go all the way up, it expects an image of 224 by 224 by 3, right? So it expects an image of 3 channels, 224 by 224 and 3 channels. But here our input that we actually have is 1 channel right there, which is our lightness channel. So it's going to fail if I just use my image as is. It expects my image to be 224 by 224 by 3. So one way is copy this L channel 3 times and attach them. In fact, some of the tricks I'm talking about, I actually did some Google search and I found I should have actually noted down this page. I took a lot of notes from this blogs and other pages when I'm training myself, on this topic. And I'm actually referring to that notes as I'm talking, as I'm training you guys. So I should have acknowledged this person, but I apologize if you are this person watching this tutorial. Please let me know so I can appropriately acknowledge you. But anyway, so this trick of just copy this. It sounds like a simple thing, but I couldn't think of it. I'm like, okay, what do I do to actually convert this into 3 channel? But anyway, I got this trick. That's the advantage of just Google searching, and then within like few minutes you find what you're looking for. Okay, let's get back to the topic. So what we did is, so we took we created an empty list, VGG features, and then we populated it by appending the prediction here. But first, let's go step by step. So we are creating this VGG features empty list so we can actually send those features into the decoder part that we're going to build later on. Okay, so let's get this VGG features ready. And how are we going to get that ready? By actually taking our X values, right? These are the lightness values, pixel values from every image that we have as part of our training, right? So we go through each and every image over there, and we convert those gray images. Again, these are all gray images, right? These are all lightness value pixel values. So we're converting those to RGB, okay? And then we are reshaping them into 224 by 224 by 3. By converting them to RGB, by default, we are actually, that's in a way, we are copying the same channel 3 times, okay? So the gray becomes RGB, and then the dimensions of our new array are going to be 224 by 224 by 3. That's it. And then we are actually predicting it under our new model, right? If you remember the new model, we just printed it out. Here is the new model, and all the way it goes down to is 7 by 7 by 512. So at the end of this should be we need to have an array that has a size of 7, 7, and 512. So we are predicting this, and we are converting, reshaping this predict whatever that array that comes out into a shape of 7, 7, and 512. That's what the step is. And we are appending all of these prediction values to our VGG features, and that's how we are populating this. And finally, let's look at the shape of this VGG features. Okay, so this is what we are doing, and I forgot where up to what point did we actually do the last time, printing X and Y shapes. So let's go ahead and run only these lines for now. So okay, so what did it say? Failed to get convolutional. This is probably because Kudi. Okay, I have no. Sometimes on my laptop, the GPU acts up, and then I get this error. So let me go ahead and kill this, and then restart the kernel, and hopefully it works. Otherwise, I'll have to switch to my laptop that has no GPU, but that's not fun. Okay, so I had to restart Spider, and obviously restarted the kernel, and so far everything looks okay. So let me get things back to the same zoom level and everything so you guys can see what's happening. So here we are. So VGG features shape is 7, 7, 512, 32 by 7 by 7 by 512. That means it matches exactly what needs to go into our decoder now. Okay, so so this is so far. Again, I'll summarize it at the end. I don't want to confuse you again. So now the decoder part is pretty straightforward. Again, you can actually go ahead and experiment with how to define your design your decoder. But again, we have our an idea, right? I mean, so the decoder is 512 features, 256, 128, 64, 64, 32, and so on. And you can design this. And again, if you want, you can go ahead and look at the summary over there. And here is the summary. So the input here is 7 after the first convolutional layer 77256, and all the way it goes to 224 224 2, and these two are our color channels predictions that we are trying to make. Okay, so this is the decoder part, and again at this step this is the encoder part, but we are actually borrowing it from VGG because it's only extracting the features, and no color information is in here right now, right? So that comes only at the final. By the way, I should have mentioned that comes only at the final prediction layer, where we have these two, one of the two predictions happening here, and our activation is tan H, or hyperbolic tangent, that goes from -1 to 1. Okay, that's why we normalize our values, input values to, I mean the A and B channel values to between -1 and 1. Again, this is the prediction. Okay, X is the input into our autoencoder. So there you, I think we are all set to go ahead, compile, and fit this. So what do we fit this to? So we fit it to VGG features as the input to our model, and the output to be where is it, to be our Y. I think we have our Y shape correct. Yeah, 32, 224, 224, 2. Okay, so that's what we need to predict. So let's go ahead and let me copy this from our other file again. So we are still using the Adam optimizer, mean squared error loss, and we are monitoring the accuracy for metrics. And what goes in is VGG features, and which is our X in a way. We replaced X with VGG features again, if you remember. And Y is Y, and let's only do for 10 epochs, and I'm going to save the model. In fact, I trained this model on 10,000 epochs, and let's load that and predict some images in a minute. But I just want to show you how this actually is working. So let's run these lines of code. My GPU is back up and running, so hopefully this should be pretty fast. As you can see, it's very fast now. If you actually have this entire encoder and decoder part like we had the last time, this was a bit slower, actually a lot slower. So transfer learning actually obviously increases your speed by a lot, because you're not going through assigning weights or biases, or training the encoder part. Okay, there you go. So that's it. And if you're curious about how this model actually works, here is the piece of code down here where let's only run this. I saved my model under the name VGG16 10,000, and it goes through image colorization to test images. So it's going through these test images. Let's actually have a look at it, and dumps the result into the VGG result directory. I have no clue why this is so slow. Sometimes I hate this Windows 10 machine. For simple tasks, it's slow. Okay, so there you go. So we have a whole bunch of these gray level images, and let's see how good of a job it actually does. Okay. So let me get back here and select only these lines. It should be pretty fast because this is just prediction. There you go. And now I should see some images under VGG result. And there it is. I'm not sure. It's not that great of a job, but yeah, it's not bad. I mean, you see something. Some images they look better than than other images. Let's go there. This one, that looks okay. The sky is blue, the grass is green, and some. Oh, this one's pretty. That's not bad, huh? That looks very good. And what else do we have? This one's also not bad. Oh, this one's also pretty good. So it seems to do good with some images compared to others, or maybe it is dark enough that I'm not seeing any anything wrong. So it still is a good idea for you to have a lot of your own images, but then for a lot of feature extraction part, if you can borrow it from existing models like VGG16 or something else, then why not go ahead and do that? So I hope you learned how to actually take existing models and what they call, do transfer learning by chopping, the model to wherever you want, and taking, again, we just chopped it off at this point, but you can actually take wherever you want, yeah, and then you can retrain that if you want. Okay, all you need to do is say equal to true when you in the beginning when we said wherever we said false, layer trainable false, go ahead and say true. In fact, you can say that the first 16 don't train them, but then train 17 and 18, right? So you can only train some of these when you import it. Hopefully you'll find time and put in some effort to learning this topic further and applying it on your own application. But I hope you learned something with this tutorial. Please like this video if you like it, and subscribe to my channel. Thank you very much for your patience and attention.